Good morning, everyone. So we have a couple more slides from chapter 8, and then we'll probably get into some chapter 9 here today. If you actually go to the chapter 9 slides, the remaining chapter 8 slides and a couple other chapter 8 review problems were added in. So if you wanted to start from the chapter 9 slides in your notes today, that might be helpful. But a couple Lewis structure examples for today. So C2H4. So hydrogen's always on the outside. Hydrogen never bridges. Sometimes it's a little confusing sometimes on how we could have a molecule like this, but the two carbons just have to be connected together, kind of like C2H6 for ethane, but here we just have two hydrogens for each carbon. Sometimes I might write this as CH2, CH2 to make sure you see the connection. There's the two hydrogens on each of the carbons. So not too tricky, I don't think, to figure out that this would be two hydrogens on each carbon. And then if we're thinking of the total number of electrons used at this point versus available, we would have 2 times 4 for the two carbons plus 4 times 1 for the hydrogens. So that would be 8 plus 4 for 12 valence electrons. And I have 2, 4, 6, 8, 10 electrons so far. And then what we could do is realize that we have 2 electrons left over that we could use to make a double bond. We were going to blow that pumpkin up later. Okay, so we can use a double bond here. Now, if you notice, carbon has 1, 2, 3, 4 bonds per carbon. And we mentioned back for like ethane when we were doing Lewis structures back in chapter 2, or just kind of sketching out the formulas of things like CH4, C2H6, C3H8, that one of the things for carbon is it likes to form 4 bonds. And we see here this is just each of the carbons forming 4 bonds. If you think about the formal charge of carbon, it's 4 minus 4 for 0. And so that's good. The hydrogen's 1 minus 1. So the formal charge is 0 all the way around. Okay, so what about something like xenon F4? So xenon occasionally can form compounds. These usually are formed at like low temperatures and very kind of peculiar circumstances. And if you warm up xenon F4, it ends up separating just to xenon plus F2 gas. So not exactly a stable compound. I don't think you're going to have this be stable at room temperature. But we would look at xenon, 8 valence electrons, noble gas, plus 4 times 7 for the fluorines. That gives us 36 total electrons. And then we have our essential xenon for fluorines. This is fun. This is like, will my arm get blown off later today? Oh yeah. The day is young too. Yeah. In fact, I'll do it now. If you guys want to hang out, that's fine. We'll finish this Lewis structure in a minute. So guys, we're going to carve this pumpkin using chemistry. This is a joke I would tell. It's like, have you ever been carving a pumpkin and you just can't wedge your fingers in to get the pieces out? And you're like, well, is there some other way to get the pieces out of the pumpkin? Seems ridiculous, right? You reach in and pull them out. But super loud, so you guys don't have to cover your ears like that one demo. Let me take the lights down a little bit. If you guys want to record, feel free. It'd be interesting to see the lights come back on afterwards. Okay. So the longer we give it, the better. The more chance. Okay. Does anybody still remember the name Gallagher? Is that a name, comedian? He was a comedian from like probably the 70s or 80s who would like smash watermelons at his comedy shows, and then the front row would have to like put up like tarps so he would get. Give a round of applause for people who actually do that. All right. They have, it's fun. They get to carve a bunch of pumpkins throughout the day because they'll eventually burn up and get destroyed. But okay, if you guys ever want to work in the demo lab, they're usually hiring at the end of the year for the following year. So if you're excited by working in a lab that gets to make the demos for class, look for these usually announcements that get posted around the buildings towards the end of the year. Okay, so let's come back to our Lewis structure. So we have xenon F4. We had counted up 36 available electrons. One of the key steps in our Lewis structure process is start with your central atom, single bond atoms, connect their complete their octets, and then count the used electrons. So that's 32 electrons. We have 8 electrons distributed around each of the fluorines. So that's 4 electrons left over. And so the leftover electrons onto the central atom. And now it looks like xenon, in fact, you would say the Lewis structure of xenon violates the octet rule by having too many electrons around xenon. Xenon would have a total of 2, 4, 6, 8, 10, 12 electrons surrounding it. The octet rule would say the max is 8, so that's an octet rule violation. But that's okay because these fluorines are electronegative. They're pulling electrons back off of xenon so that it really doesn't have to have that many electrons surrounding it. So it's going to pull electrons more closer towards itself. And then the formal charge of xenon would still be 0. So we'd have 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding xenon for a neutral charge. Same thing with the fluorines. So 0 formal charges all the way around for xenon F4. So another example would be BrO3 minus. And again, these are just more exercises and just making sure we kind of are aware of the rules. So 3 times 6 plus 1 plus 7. And so that gives us a total of 18 plus 8, that's 26 electrons. And so we have bromine, 3 oxygens, and then that's 24 electrons used. Now it's important to not really shortcut this counting process here because we might miss the 2 electrons that are placed onto bromine through the process. We have a lone pair on bromine. And then this is actually our octet rule Lewis structure for this molecule. And so we have minus formal charges for the O's. We should have 6 electrons around O's for a neutral charge. And we have 7 electrons surrounding each of the O's. Bromine's charge for a formal charge would be, it should have 7 electrons surrounding it, and it has 1, 2, 3, 4, and 5. So that bromine only has 5 electrons around it, so that's a plus 1. a plus 2. 7 minus 5 is plus 2. So minus, 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 plus 2. Overall charge is minus 1. So the formal charges should sum up to the overall charge, and they do. So minus 1 times 3 plus 2 is minus 1. Now, so this would be, like if we ask a question on a test, it's like for the octet rule Lewis structure, or for BrO3 minus in the Lewis structure that satisfies the octet rule for all atoms, describe the Lewis structure. We'd have 3 single bonds between bromine and oxygen, and then 1 lone pair of electrons on bromine. And we'd have 3 lone pairs on each O. Now, we could also then say, well, what about reducing magnitudes of charge through making double bonds? And so bromate here does have one other acceptable Lewis structure. That would be the one that satisfies the formal charge rule. I'm going to write it over here. So we'll have bromine, double bond O, lone pairs around the other O. We keep the lone pair on bromine. So we're just moving 2 electron pairs in to be double bonds. And so this would be our formal charge rule, Lewis structure. And then the formal charges would work out here to be 0, 0, because those are 6 minus 6. And then bromine will be 7 minus 7 for 0. And then we have 1 minus 1 charged O in the Lewis structure. And then we're going to have resonance kick in, and we're going to have the double bonds kind of resonate through the molecule. So we'd still have, if we ask the question, are all the bonds identical in length in bromate? The answer is yes, no matter which Lewis structure you're looking at. So we would have resonance here. So we'd have 3 resonance structures. And then all the bonds in BrO3 minus would be equal in length. So remember, resonance is an all-time distribution, so that extra, or these 2 extra pairs would be distributed across that single bond at all times. So we'd really have, if we want to describe the bond, I don't know if we'd even ask this question, because but I think it just gets you to see how the bonds would equalize in the structure. But we'd have 2, 4, and then 5 bonding pairs of electrons spreading across those 3 bonds. So it's weird, it's like a 5/3 type bond order. But it's like clearly showing you that the bonds aren't quite double in length, they're not quite single in length, they're somewhere in between. And so again, we wouldn't say for bromate which Lewis structure of those 2 is best. We would just say one of them is the octet rule Lewis structure, the other one's the formal charge Lewis structure, one that minimizes the magnitudes of formal charge. The very last section in Chapter 8 is on bond strengths. Now, we talked a fair bit about bond strengths in Chapter 5, where we were using them to calculate or approximate delta H's of reaction. We'll remind you of that problem, but we'll also mention that we've already covered that problem, so we're not going to recover it for Chapter 8. But we see our bond strengths here for carbon-hydrogen single bonds. So most of our single bond strengths are in that 200 to 400 kJ per mole range. And then our double bonds are in that stronger range of about 600 to 800 for double to triple bonds. So triple bonds are stronger than single bonds, double bonds kind of in the middle. So our carbon-carbon bond longer, carbon-carbon bond short, double bond shorter. So we talked earlier about how bond length is affected by bond type. So this is the shortest bond of the 3, and it's also the strongest bond, hardest to break. Takes the most energy to break, and then the single bond is the longest bond, and it's the weakest bond, which I think makes total sense, right? Having more electron pairs to bring the nuclei together strengthens the bond, shortens it in the same process. And so in each case, like O2 double is 495, but the OO single is much less. The OO single bond is really weak, 146 kJs per mole. So stronger bonds are strengthened by increasing the bond order, or the type of bond between the atoms. If we compare more directly with some bond lengths for single, double to triple, the bond length decreasing towards triple for carbon-carbon bonds. Carbon-nitrogen does the same trend, where we're, that's interesting, it actually, so we're decreasing, but not much, from carbon-nitrogen single to carbon-nitrogen double. And then we decrease a lot to the triple bond. Carbon-oxygen bonds follow the same trend. So you see the same trend being followed, that single bonds longer and weaker, and then triple bonds shorter and stronger. So this is the type of problem that we covered in chapter 5 for approximating delta H's of reaction. So we're not going to recover this here in chapter 8, so we've already talked about this type of problem. The only thing that we can maybe do, and we'll probably revisit a problem like this when we review for the final, is back in chapter 5 when we introduced this topic, we'd have to show you structures because we maybe wouldn't know how to sketch a Lewis structure and understand the bonding in these molecules. But when we revisit this problem for the final, we'll just, of course, have the reminder that when we see CO2, we know now that this is, of course, double bonded on both sides. So we can work out the geometries, or really the Lewis structures of the molecules, to get the bond type, and we don't have to show them to you here once we've gone through Lewis structures. And so then this was the last problem in the notes, and then there are a couple review problems we'll do after this from chapter 8 here today. But this question's here asking us that we, sort of, according to their Lewis structures that obey the octet rule, we're going to rank the NO bond lengths in order of increasing distance based on their bond orders. And so we have NO minus, so that's 5 plus 6 plus 1. So that's 12 electrons. And so that's going to be like O2. That's going to be a double bond. For diatomics, I'm just trying to satisfy the octet rule. So the only way I can satisfy the octet rule for both atoms to give them each 8 electrons is with a double bond. And then we might recall that this was kind of peculiar in that we end up with a -1 formal charge on N, because it was 5 minus 6. And a 0 charge on O, 6 minus 6 for the neutral charge. And so we have a double bond for NO minus. Let's compare to NO2 minus and to NO3 minus. For NO minus, I probably should have counted the electrons first, but so we're going to do 5 plus 6 times 2 plus 1. So that's 18 electrons. And then find the central atom, single bond, lone pairs on the outer atoms, and then count electrons. So that leaves 2 electrons behind. So lone pair onto nitrogen. So sometimes on practice exams and on real exam and quiz problems, you might see a question that says, consider the Lewis structure of a molecule and which Lewis structure in pictures is correct. And so you might look at the choices and see which one's correct. Now, in my view, whenever you see a Lewis structure, if you just go through the rules and then sketch your Lewis structure and then compare and look to see which one matches, that works pretty well. But I just wanted to make sure that I give this tip that if you're looking at Lewis structures and trying to see which one looks like the best Lewis structure where you haven't gone through the rules to sketch the Lewis structure yourself, one thing you might do is just count the electrons. So one way a Lewis structure can be shown to be wrong would be just having too few or too many electrons for the structure that's shown. So when you count the electrons, it's like this number has to be shown in the structure for it to even be considered to be a valid Lewis structure. Like if I only had 16 electrons shown for NO2 minus, it's not NO2 minus. It's NO with some other charge. It would be NO plus, NO2 plus actually. And so one way to make sure a Lewis structure is right is by double checking the count of electrons. But then of course the electrons have to be distributed correctly. Right here we'd have a positive formal charge on nitrogen. And we'd have negative electrons that we can pull in, make a double bond. So we make a double bond here. Leave the other one single. Keep our lone pair on nitrogen. And then of course we can have resonance. So we can resonate the double bond across the other side at all times. And both those bonds end up, of course, having identical length. And the bond length would be representative of a bond that had an order of 3 bonding pairs of electrons spread across those two covalent bonds. So the bond order would be about 3/2. For NO3 minus, 5 plus 3 times 6 plus 1, that's 24 electrons. So no lone pair for nitrogen because that's all 24 electrons, but I do now have a 2+ formal charge, and I can make a double bond. And then that knocks the formal charge on nitrogen down to +1, because it's 5 minus 4. And then the oxygen that we made the double bond is 0. The other two are negative. Then at this point, I have to stop for nitrogen for 2 reasons. One, like, I don't even know if we should throw this into the problem where we say in the problem that the Lewis structure should satisfy the octet rule. Because remember, a second row atom can't expand its octet anyways. Like, if we wanted to make a second double bond here to reduce the formal charge, that just doesn't work for nitrogen because it's in the second row. So we can't really do that anyways. And so we're going to leave that bond single no matter what. And then this is our best Lewis structure here. And so this is the best Lewis structure, or at least one of the 3 best Lewis structures for nitrate, the other 2 being this one here where we kick the electrons back onto the other O, and then where we make the double bond over here and kick those electrons back over to the minus. And so our nitrate here is sharing 4 electron pairs. So we have 4 bonding pairs. So 4 bonding pairs of electrons across 3 of the bonds, 3 covalent bonds. That gives us an order of about 4/3. And now, again, I'm sure this makes sense, but a single bond is 2 pairs of electrons across 1 bond, so that's single. Carbon-carbon double, or any double bond, would be 2 pairs of electrons across 1 bond. And then a triple is just 3 pairs across 1 bond. Just making sure that we see what bond order. Sometimes it's a little confusing what I mean by bond order. It's just the average number of electrons being shared across each of the bonds. And so nitrite, or whatever NO minus is, the NO minus double should be the shortest. And then our 3/2, 1.5 bond order, should then be the next longest. And then we're closest towards single with the 4/3 at 1.33. Okay, and so this is the lesser bond order, so this is the longest bond here, and then 3/2 is in the middle. So it should go 1, 2, 3. Now, it might be worth mentioning that there's more to bond lengths than just bond order. There's like, these atoms do have partial charges, and there's still electrostatic attractive forces. If you look up these actual bond lengths for these molecules, they're all pretty similar, but I think they do follow the trend. But nitrate and nitrite, pretty similar, but you also have to imagine that there's the charge on the O, the charge on the N can actually affect the bond length too, in addition to the bond order. But we're told in the problem also that we're making this bond length trend based on the bond orders. So when we're making the length based on the bond orders, we're just comparing 2 versus 3/2 versus 4/3. Okay. So just a couple of review problems. One of them, I just thought to look at lattice energy. So remember, lattice energy is the energy associated with any of these compounds here as solids. Ionic compounds have strong forces of attraction. So ionic compounds are solids at room temperature due to those strong forces of attraction. So say calcium sulfide would be a solid. The lattice energy would be the energy associated with that compound dissociating into its ions. So calcium 2+ and then sulfide 2-, but specifically as gases. So it's really just like if you imagine taking the compound and separating the ions, gives you a measure of how strongly attracted the ions were together in the ionic solid where it's plus minus, plus minus, plus minus, alternating throughout the structure. So the delta H of this reaction corresponds to be equal to the lattice energy. So lattice energy would be 1 mole of an ionic compound as a solid forming its gaseous ions. And then if you think of the energy of electrostatic attraction, kappa Q1, Q2, divide by D. So the electrostatic attraction equation, or Coulomb's law, says that if you have a minus and a plus, then you have a negative. Your energy of attraction is negative, so the particles are attracted together. So I like to think of the magnitude of the attractive force. So think about how negative it is would be impacted by how positive and negative the charges are. So the more plus, the more negative the charges, the greater the magnitudes of charge, the stronger the attractive force, therefore the harder to separate. So the lattice energy, if you think about the lattice energy, it's just directly proportional to this electrostatic attractive force. So it's just proportional to the magnitude of this energy of attractive force between the ions. And then also, if you put the ions closer together, make the ions smaller, actually makes them more attracted together, makes them harder to separate. So if you have a plus and a minus that are a mile away from each other, how attracted can they be? If you have a plus and a minus that are an angstrom apart, that sounds to be a lot better. So the closer the better, the smaller the ions, put the charges closer together. And so whenever we're looking at a comparison like MgO versus CAS, they're both 2 plus 2 minuses. We're just making that based on the row the elements are in the periodic table. And so MgO versus CAS, this is all about MgO being smaller. So the 2 plus and 2 minus charges can get closer together. So MgO2 minus maybe looks something like this. And then maybe calcium sulfide to show it to a bigger scale, but maybe calcium and sulfide, just bigger ions further away from each other, therefore easier to separate. I'm actually looking for, I tricked myself here, for the lower lattice energy. So the lower lattice energy is the bigger one. So I was answering the stronger is the MgO. The weaker attractive force is the calcium sulfide. So calcium sulfide has a lower lattice energy to separate into its ions, therefore weaker ionic bond strength. MgS versus aluminum nitride, 2 plus 2 minus versus 3 plus 3 minus. 3 plus 3 minus, much better. Stronger attractive force between a 3 plus and a 3 minus, so MgS would have the lower lattice energy. So the higher the magnitudes of charge, the more attracted the ions are, harder to separate. And then I wanted to show this one here so that whenever we see a plus minus versus anything else, the plus minus is always lower. Like we look at size comparisons when the charges are identical, but the magnitude of charge difference is a huge difference. The size difference isn't a huge difference, it's a small difference. So the charge difference here of the 2 plus calcium will trump the relative small size of lithium and fluoride. So you might look at lithium fluoride and say, lithium fluoride, that's really small. Isn't that going to be really strong for the plus minus? And for the plus minus, it would be the strongest ionic compound there can be. But the 2 plus calcium with bromide will give it a higher lattice energy, just to having almost a double lattice energy due to that double magnitude of charge. So the charge makes calcium bromide a lot higher. So lithium fluoride would have the lesser lattice energy. So it just goes to show when you're comparing and ranking lattice energies, you're kind of ranking by charge first, and then within the charges, you're looking at the relative size of the ions. So I mentioned this problem last time, maybe we'd take a look at it, so I figured why not review calculating charges using a dipole moment. These problems are very extraneous, but I think they're very interesting with a diatomic molecule because you can come up with a fairly simple equation that can allow you to calculate the partial positive and negative charges. Helps you kind of see what we mean by partial charge too. So we did a problem for HF in class before, and the H was plus 0.41 and the F was minus 0.41. When we're thinking if it were H plus and F minus, that this would have been, plus 1 electron, minus 1 electron, but it ended up being plus 0.41, if you recall, minus 0.41. Give us an idea of how positive and negative do we mean by those partial charges. HF's really polarized, so this is a pretty big difference. Most of our plus minus charges, partial charges, are going to be smaller in magnitude because this is a really big difference. These H and F have a big difference in electronegativity. Now Cl and O, they're not tremendously different by electronegativity, but oxygen's the second most electronegative element, fluorine's the most. So oxygen's going to pick up presumably the negative charge here. We had this Lewis structure. If you recall, we were looking at the Lewis structure before, and we were trying to figure out, should we go with this structure here with a minus and a plus, Or should we go with this Lewis structure here, which had oxygen with, we have to have chlorine with one fewer electron here. So Cl and O only have 7 plus 6 electrons, so we have an odd count of 13 electrons. So our 13 electrons, do we leave chlorine deficient of an octet, which gives it that positive charge? Oxygen's charge would be minus in the Lewis structure we sketched already. Or do we give chlorine its full count of electrons, give it 8 electrons around for a 0 charge, and then oxygen here would be 6 minus 6 for also 0. And so if you recall, last time we were weighing or talking about how, well, we want to reduce the magnitudes of charge if we can. If there's some way to go 0 and 0 formal charges, that's better than +1, -1, even if the minus ends up on the more electronegative atom. And one of the things I had mentioned is that this structure is better because then we can think about the polarity of the bond being more shaded towards the more electronegative O, so that O can pick up a partial negative. And that if we thought this was the Lewis structure that was best, then we would probably think O goes beyond even -1 charge. And so just setting the problem up, what I had said last time was, well, if we knew the bond length and the dipole moment of this molecule, we can then calculate the charges on the atoms and kind of see which Lewis structure makes more sense. And that's what we have in this problem here. So we have the molecule ClO has a bond length of 1.57 angstrom and a dipole moment of 1.24 debye. And then what are the charges on Cl and O? And we're given, and whenever if you have to do this problem in a test, we give you the conversion for dipole moment into debye from coulomb meters. Coulomb's the SI unit of charge, meters the SI unit of length. So this is the SI units for dipole moment would be coulomb meters, but debye is a more common unit. And then we're also, and a common value to give you on the test is the conversion for the electron charge into coulombs. And so the equation is charge times bond length is dipole moment. So mu, the dipole moment, is Q times R. It's the charge being separated across some particular distance. And so if I want to calculate Q, I'm going to take the dipole moment, divide by the bond length. But then we just have to do some accounting for units. And then I should mention that Q would be the plus Q for the lesser electronegative chlorine, and then minus Q for the more electronegative O. So Q is the plus and minus charges that are being separated across the molecule. And so then we calculate from the bond length, or excuse me, the dipole moment first, 1.24 debye times 1 debye is 3.34 times 10 to the minus 30 coulomb meters. Then we're going to divide that by the bond length, 1.57 angstrom, where 1 angstrom is a 10 to the minus 10 meter. And we could stop and if we stop and calculate at this point here, we'd have the charge of the atoms in units of coulombs. Well, let's just go over to the charge relative to the charge of an electron. So this is where we use the electron charge. So we go 1.24 times 3.34 e minus 30. I divide by 1.57 e to the minus 10. So I hit enter. That's 2.64 times 10 to the minus 20 coulombs. So we're not quite to 1.602 times 10 to the minus 19. So let me just divide my answer by 1.602 e to the minus 19. And I get 0.164 electron charge units. Technically with rounding 0.165. And so what that would establish is that the charge on oxygen is minus 0.165 units of charge relative to the electron, And then chlorine's charge is plus 0.165 units of charge, again, relative to the electron. I find sometimes this is confusing to the students. Just remind yourself that plus 1 minus 1 is plus 1 electron minus 1 electron. So this is really, when we say plus 1 minus 1, that this would be minus 1 electron plus 1 electron. So we're just saying it's 0.165 electrons, so a partial negative on oxygen. So if you recall, when we looked at this Lewis structure, I think it was on Friday when we looked at this, I had said it wouldn't surprise me if the charge on oxygen wasn't even anywhere near like half a unit of negative charge. And when we're weighing these Lewis structures, it's like this negative charge here doesn't really mean anything. We want to minimize the magnitudes of charge when it's possible, so we did so with the 0, 0. Then we can think bond polarity kicks in. Oxygen is a little bit more electronegative than Cl, so it becomes a little bit more negatively charged. It has some partial negative charge. So this example here, review of this problem, but then also connecting it back to really why we want to reduce the magnitudes of charge and how it relates to what ends up being the real charges of Cl and O in this problem here. Okay, so with that, a lot of the, there is one more problem to review from chapter 8, but I was going to say for chapter 8, the last thing to review are Lewis structures, but we're going to keep doing Lewis structures in chapter 9. So we're going to reinforce Lewis structures with a lot of examples that we see when we get into chapter 9, where we're going to start to get into the geometries of molecules. So what I want to think here on this problem is that when dipole moment is Q times R, I just want to think for a minute and maybe even just, I don't know how much we talked about what really impacts dipole moment and polarity. Like the Q value, this is really related to electronegativity differences. So the greater the difference of electronegativity, leads to higher magnitudes of partial negative charges and partial positive charges being distributed across the molecule. And this would go for all bonds, not just diatomic. So if you're looking and comparing like BF3, for example, versus like CF4, where boron's electronegativity is lower than carbon, so the CF bond probably not as polar. So this is probably less polar than BF3, or than the BF bond. Because boron's less electronegative than carbon. So it's like F2, not polar at all. OF a little bit polar, NF even more, CF4 even more, BF3 even more so. And so what this would probably tell you is that the partial negative on fluorine is going to be higher than the partial negative is on CF4. You know, that, like, the electronegativity difference is impacting those partial charges. Now, for diatomic molecules, mu is like a measure of the charge being distributed, but it also is a factor for the bond distance. So I don't know if it's, sometimes we say dipole moment's a measure of polarity. I think Q is really the measure of polarity. I think when you're looking at Q is the one that, as the bond's more polar, the charges are becoming bigger, and then the mu is just then a function also of the bond distance. You know, so there's like more factors into the dipole moment and its value. So if one molecule has a bigger dipole moment, not necessarily more polar, because it could just have a longer bond length. Because as bond length goes up, as the atoms are further away from each other with the same charge being distributed, then you would have a greater dipole moment. And you would probably say if a bond just happens to be longer, but maybe the Q values are a little bit lower and ends up with a larger dipole moment, does that mean it's more polar? I think the polar question is the electronegativity difference. So I think the polarity trend is really ranked with the Q value difference, and that's coming off our electronegativity differences. But I also wanted to point out that if you had the exact same charge being distributed now across a longer bond, that actually makes the dipole moment bigger, just because dipole moment is proportional to bond length. Okay, so with all of that said as a preamble, we're just comparing, compared to ClO, do we expect BRO to have a longer or shorter bond? Well, bond length trends will just come back to, for both of these molecules, they have a single bond. So when you're comparing bond lengths, they have the same Lewis structure. So we're back at the same kind of Lewis structure we had on the last slide for each of these. So if we want to compare bond length trends, we're just making sure they're both single bonds. Bromine being bigger makes it have a longer bond. So the BRO bond is longer than the CLO bond. The magnitudes of partial charges. Well, let's think about the electronegativity differences here. So CLO versus BRO. Oxygen's really electronegative, bromine's less electronegative. And so BRO should have greater magnitudes of partial charges because there's a greater difference of electronegativity. So in terms of our electronegativity, we just get a bigger difference. Than for chlorine. So the Q we'd expect for BRO, the charges we get from the electronegativity differences would be greater than the charges we would get for the Q for CLO. And you could look up the bond length and the dipole moment, and I did this on the side. I think it was like 0.18 or something. It was a little bit higher magnitudes of charge for the BRO molecule compared to CLO. Probably not useful for us to go through that calculation again, but you could, in theory, just go through the calculation we did in the previous page, but for BRO, and it has a slightly greater magnitude set of charges. And then what about its dipole moment? So the Q value is higher, the bond length's longer, so its dipole moment has to be bigger. So it has a greater dipole moment as well. So we can think about how all these values kind of relate to each other based on the properties of chlorine versus bromine, the properties of electronegativity difference, and then putting it all together in terms of the dipole moment. Okay, so I think that was our last Chapter 8 review problem for this point in the class. We'll look at some more review problems from Chapter 7 and 8 when we get closer to midterm 3. I think last week I mentioned midterm 3. I confused some of you guys. I said it was in 2 weeks. It's really 2 weeks from today. So 2 weeks from today we take midterm 3. So we have the rest of this week's lectures. Next week we also have a Monday, Wednesday, Friday's a holiday next week for Veterans Day. So we don't have lecture Friday again before our Monday midterm. But we'll try to get some review topics in next Wednesday and then also Monday, the day before, or the day of the test. Okay, so the last chapter covered for midterm 3 is Chapter 9, which gets into the geometry of molecules and into some theories of bonding towards the second half of the chapter. So here we're going to talk about shapes of molecules. VSEPR is valence shell electron pair repulsion. It's a way we can think about the geometries of molecules from the electron pairs repelling each other. So if you start thinking of something like BF3 is a good example, you have a Lewis structure where the repulsion comes from, well, it comes really from two things. It comes from the electron pairs and those bonding pairs around boron, and then also from the atoms themselves. So you have the repulsions of the nuclei, the repulsions of the electron pairs. So valence shell electron pair repulsion theory says it's really these bonding pairs that repel each other. These are electrons that are negatively charged, so of course those electrons would repel each other. And so they want to get as far away from each other as possible. So VSEPR theory is going to take us through having sort of 2 domains around the central atom, 3 domains, 4 domains, up to 6 domains around the central atom, and how those domains can spread out and use the space around them to minimize their repulsions. From there, we'll talk about molecular shape and polarity, where something interesting happens for BF3. The BF bonds are certainly polar. We just talked about it. They're really polar. We get these big partial negative charges. Now, what would you do if I told you that BF3 is perfectly nonpolar? That this is a nonpolar molecule? At first glance, you'd say, well, that doesn't make any sense. And it, in some ways, doesn't make a lot of sense. But you have these dipoles opposing each other in the molecule. And so if you imagine having a dipole moment pointing this way, let's even look at CO2. Maybe real quick, CO2 is a good example, where we have these 2 dipole moments that oppose each other perfectly. And then if you think of dipole moment being a vector this way versus a vector this way of equal magnitude, those vectors serve to cancel each other out. So the dipole moment of this molecule ends up being perfectly 0. Same thing with BF3, perfectly 0. Now, they still have polar bonds. but molecular polarity is going to depend on shape. So we're going to have to understand shape. We're going to have to understand how that shape dictates a role in something like a property for dipole moment. One way you can start to picture, if you're sitting here thinking, I still don't get why these would necessarily be nonpolar. Imagine we have a positive charge. Like we can just have a positive charge near these molecules. Would the molecule like flow towards that charge, or would it just like start spinning where all the atoms fight for the charge? And something like BF3 would just turn into like a fan. It would just start spinning. Same thing with CO2. It wouldn't flow towards a charge. To flow towards a charge, we need like a plus side and a minus side of the molecule, where the minus side of the molecule would flow towards that charge. So we need like a net type of molecule where there's some charge differences built into the molecule. Not to necessarily belabor the point of molecular polarity before we get to that part in the class, but I think it's good to kind of have a picture of where it is that we're heading and start to picture some things that make sense or can make sense right off the bat. If you picture water, we have partial positives on your hydrogen because we have these polar bonds pointing in towards oxygen, partial negative charge. I put a positive charge over here. Oxygen can flow towards that charge because it doesn't have other atoms that are fighting for the charge and making it spin. So we can have oxygen flow towards a positive charge because we do have a negative end in our molecule. The two vectors would serve to add a dipole moment pointing towards oxygen that in this picture is like straight up. So we have a net dipole moment. We have a polar molecule. Now, where this really matters is the properties of molecules are greatly dependent on things like their ability to be attracted to each other. So water molecules, because they have this built-in charge difference, have a much stronger attraction for each other. So if you think of two adjacent CO2s, there's really no special attractive force between two CO2s just because the bonds are polar. You need the molecule to be polar. So two water molecules, if we stack them on top of each other, we can see the hydrogen bond start to form if you've seen this before. The hydrogen bond, the H and the O, attractive forces for each other. They can have and experience that attractive force because of those built-in dipole moments. Two adjacent BF3s, it's just like a big, almost like a big sphere of negative charge. It just more or less repels itself than it does attract itself. So we get more attractive forces between polar molecules. We'll see that play out when we get into chapter 11 later. Okay, so then we'll talk about some covalent bonding and overlap theories. So talk about how bonds can be maybe understood through the overlapping of their atomic orbitals. And then that'll lead into talking about hybrid orbitals, multiple bonding, things like pi bonds, if you've heard about those. We'll give a description of what pi bonds look like. And then we'll get into molecular orbital theory, so try to describe the bonding in like second row diatomic molecules. There's really an interesting property of oxygen that isn't really understood through any bonding theory to the point of until we get to MO theory to describe oxygen. Oxygen has a really peculiar set of properties, and it has unpaired electrons somehow. So when we look at oxygen, we look at the double bonded structure. We have these electron pairs here. If I told you that oxygen had two unpaired electrons somewhere in its structure, it'd be like, well, where are they? Because these electrons here look like they're spin paired. Bonds are usually spin paired. So these electrons all look spin paired. So where are the unpaired electrons? How does the molecule have unpaired electrons? Well, that leads into MO theory. So I think the main reason we introduce MO theory to you guys, and we'll talk about it so we can understand an important property of oxygen, and then try to then link back to some of the other theories we talked about. So if we introduce you a theory that for O2 fails, we probably then want to look back at the theories and try to understand how they still end up working for most other molecules. And that maybe there's a few molecules that are asterisks and have to be understood through more advanced methods, but the other theories that we teach you are generally applicable and work well for most of the molecules that we model with those models. So let's talk about molecular shape here. So one thing that's really important to drive home here is that when we sketch a Lewis structure, we're not always intending to show molecular shape. So like if I show a structure for CCl4, let's say this way here, and I just sketch a Lewis structure like this, and I have my chlorines with their lone pairs, I had 32 electrons to distribute. I have 32 electrons around this molecule. That I'm not trying to say, when I sketch a Lewis structure, that CCl4 is flat. So one thing we have to make sure that we see is that a Lewis structure is really just trying to tell us what are the central atoms and what are the type of bonds that are connected to them, 4 single bonds here. When we get into shapes, we're going to then have to think, how do those shapes distribute themselves into 3 dimensions? So let's just have in the back of our mind, a Lewis structure is not always meant and often won't show us anything close to the real geometry of the molecule. So we have to be careful sometimes to think when we see a structure, you have to think, if it's a Lewis structure, it's probably not necessarily the 3-dimensional shape of the molecule. We then have to use the Lewis structures to help us determine the shape. And so here's some shapes of molecules based on a few geometries that we see. CO2 is linear. SO2, though, if we give sulfur has 2 more valence electrons than carbon. So sulfur ends up having 2 unpaired electrons on the central atom. That kicks it into a bent structure. We'll see why in a little bit, but this will give it kind of 3 domains that are distributing across its molecule, kicking it into kind of a trigonal planar geometry, and the molecule ends up being bent. So the bond's not linear, it's bent. SO3, like BF3, takes the shape of a trigonal planar structure, so perfectly planar. These bond angles here would be perfectly 120 degrees. The CO2 is perfectly 180. NF3 takes a trigonal pyramidal shape. We have a lone pair also on nitrogen kicking it into this geometry. So having knowing molecules when they have lone pairs will help us understand why they adopt their shapes. ClF3 is interesting, it adopts a T-shape. It actually has 2 sets of electron pairs in it. And so we'll talk about why these molecules take these shapes and how we can know this. This is just a few examples of some different types of shapes that we see for when we have 2 versus 3 atoms connected to a central atom. And so let's look back at CCl4. So again, we could show you like a Lewis structure, and again, it's not really a flat molecule. So sometimes we see this Lewis structure and we think it's trying to portray like some sort of square planar structure, and it's not. It's just showing us 4 single bonds around chlorine. And so what ends up happening is those 4 domains will try to separate into the shape of a tetrahedron. And so what ends up happening, the way we can sketch this with a structure would be that we have a chlorine going back and then a chlorine coming out at us, and then these 2 chlorines in the plane of the page. And the bond angles end up being perfectly 109.5 degrees for the trigonal, for the tetrahedral geometry. So we have perfectly 109.5 degrees all the way around. All the bonds are identical in type. They're all single bonds. They all have the same length, 1.78 angstrom. And then the tetrahedron name, oddly, doesn't come from the fact that there's 4 chlorines attached. It actually is from the shape of the structure you get if you connect all the chlorine atoms. So if we connect these chlorines, you get a 4-sided figure. So you get a tetrahedron emerge on the outside of the shape. So the tetrahedral or tetrahedron shape is actually coming from the connection of the atoms on the periphery of the molecule, giving the 4-sided shape. We can see a space filling model where this might help us think that our partial negatives on those chlorines are going to be hard for them to fight for a positive charge. It's going to be hard for 2 adjacent CCl4 molecules to have any built-in attractive forces. This molecule is going to be perfectly nonpolar. We'll come back to polarity a bunch of times in this chapter, but I just wanted to see us right off the bat, since we've already talked a little bit about polarity trends, that we can already predict that this molecule should be perfectly nonpolar. You can sort of see it's just a big ball of negative charge. There's no positive charge end of this molecule anywhere that we can see. The positive charge is all in the middle. We need it to be somewhere in the periphery of the molecule. And so then this is probably the way I sketch it on paper, is with a set of wedges. And so we'll just end with this slide here. So when we start getting into valence shell electron pair repulsion theory, it'll just be a matter of trying to think, how many domains do we have about a central atom? If we only have 2 domains, then those domains have to go linear. So for CO2, this is perfect. It has 2 domains, this domain, that domain. They go perfectly linear. And then if we have 3 versus 4 domains, then we go trigonal planar for 3, and we go tetrahedral for 4. So we'll get into some variations within trigonal planar where some of those domains are electron pairs, and then we'll get into 5 and 6 domains when we return on Wednesday. So we'll get into some more shapes as we go. All right, guys, that's all for today. Have a great day.